Sea turtles dance when their superpower leads them to food. Sea turtles are renowned for their incredible migrations, traveling thousands of miles across vast oceans with few visible landmarks. Now, a new study published Wednesday in the journal Nature reveals loggerhead turtles, the most abundant sea turtle species nesting in the United States, learn the magnetic fields of specific geographic locations. This superpower likely helps them get back to ecologically important areas for nesting and feeding. While earlier research has unveiled turtles consistently revisit specific sites and also use magnetic fields to navigate. The researchers said this study is the first of its kind to determine loggerheads memorize these magnetic fields, particularly ones associated with food sources, to return to once they finish migrating. Researchers found captive juvenile loggerheads respond to magnetic conditioning by what the team described as dancing in anticipation of food in fields where they were previously fed, indicating they associate magnetic cues with feeding sites. The study also unlocked a key finding in turtle navigation. Loggerheads rely on two distinct magnetic systems, a magnetic map for tracking locations and a magnetic compass for orienting direction. When loggerheads are exposed to radio frequency, or RF waves, the same type of radiation emitted by devices such as mobile phones and radio transmitters, their magnetic map remains stable, while their compass is disrupted. This revelation raises conservation concerns, as boating activity and device usage near nesting beaches may interfere with turtles' ability to migrate. According to lead study author Dr. Kayla Goforth, a postdoctoral research associate in the Department of Biology at Texas A&M University, who worked on the research as a doctoral student at the University of North Carolina, Chapel Hill. Researchers suggest minimizing RF waves in key turtle habitats to help protect these ancient sea creatures. What makes turtles dance? Turtles can detect all-Earth strength magnetic fields ranging from around 25,000 nanoteslas to 65,000 nanoteslas, a measure of magnetic field intensity, according to Goforth. To understand the magnetic receptors of turtles, researchers collected 14 to 16 newly hatched loggerhead turtles each August from 2017 to 2020. The turtles emerged from 8 to 10 different nests from Bald Head Island, North Carolina. The team housed the turtles in individual tanks with controlled water temperatures and a standard diet to simulate natural seawater conditions. Previous turtle experiments have used magnetic intensities with at least a 2,000 nanotesla field difference, but Goforth and her team chose locations along the U.S. East Coast throughout the Atlantic Ocean and developed a coil system to produce fields between 2,000 and 10,000 nanoteslas for variation. Over a 2-month conditioning period, the study team placed the turtles in small buckets of artificial seawater and exposed them to 2 different magnetic fields for equal durations. One field matched the magnetic force of a site in the Gulf of Mexico and was associated with food, the rewarded field, while the other simulated the magnetic flux of a site near New Hampshire and had no food, the unrewarded field. Once the conditioning ended, turtles were tested again in both magnetic fields, but this time neither contained food, allowing researchers to determine whether the turtles had learned to associate the rewarded field with feeding. In the rewarded field, all the marine reptiles exhibited some extent of turtle dance behavior, which included tilting their bodies vertically, holding their heads near or above the water's surface, opening their mouths, quickly moving their front flippers, and sometimes even spinning in place, according to the study. To confirm the consistency of these findings across different sites, the researchers conducted the same experiment using magnetic fields that mimicked those off the coasts of Cuba versus Delaware, Maine versus Florida, and 2 additional locations. In each of the 5 trials, about 80% of the turtles showed more dancing in the rewarded fields compared with the unrewarded, demonstrating that this skill is used globally, not just in one specific location. While the turtle dance is particularly charming, Goforth noted this behavior likely only occurs in captivity. However, the movement pattern provides a useful measure to show whether the turtles learned the magnetic field and correlated it to food. After the initial experiment, the scientists tested 16 turtles again for months later to evaluate their long-term memory. Even without additional reinforcement, 80% of the loggerheads showed greater dancing in the rewarded field, although the overall amount of movement was lower, Goforth said. Turtles likely remember magnetic conditioning for a much longer duration, Goforth noted, since most loggerheads leave their nesting beach as hatchlings and return around 20 years later to lay their first nest, using Earth's magnetic field for navigation. Once the researchers established turtles respond to magnetic fields associated with food, they wanted to determine whether turtles utilize the same or different biological systems for their magnetic map knowing where they are and their magnetic compass knowing which direction to go. Using radiofrequency waves, a type of energy that can disrupt biological sensors such as the ones birds use to detect Earth's magnetic field, researchers tested whether the turtles could still detect their magnetic map and magnetic compass. One group of turtles was tested without RF waves, while the other was tested with RF waves. Normally, turtles swim in a certain direction depending on the field they live in to stay within the right ocean currents for migration. However, when RF waves were present, the turtles swam randomly, indicating their compass was disrupted. Their ability to recognize the magnetic map or food-associated locations remained intact, however, even with RF interference. This understanding provides additional information towards figuring out how sea turtles and other animals are able to navigate hundreds and thousands of miles across oceans that don't have obvious physical features to help with navigation, said Dr. Daniel Evans, a research biologist with the Sea Turtle Conservancy, via email. Evans was not involved in the study. To investigate further how turtles interpret magnetic cues, the study team examined the two key features of Earth's magnetic field: inclination, or the tilt of magnetic field lines relative to Earth's surface, and intensity, or the strength of the magnetic field. The researchers generated mismatched magnetic fields by combining the inclination from one geographic location with the intensity from another, swapping the values throughout the trials. Turtles did not recognize a place unless both inclination and intensity matched, proving they rely on a combination of these factors to determine their location. This latest research reveals that, similar to birds and amphibians, turtles also rely on dual magnetoreception systems, which could provide further insights into other migratory vertebrates. Looking toward sea turtle conservation, the most important conservation takeaway from this research is that RF waves produced by electronic devices negatively affect sea turtles' navigation, Goforth emphasized. If turtles reside in ocean areas with heavy boat traffic or come to beaches to nest where people use phones frequently, their navigational senses could be disrupted. Companies and individuals can take proactive measures by limiting device usage on the water or at beaches to minimize disruptions to sea turtles. From a conservation standpoint, we now need to consider potential impacts of human activities on these different mechanisms, Evans said. The areas sea turtles keep returning to are important for those turtles, and these areas need strong consideration for protection and conservation.